So we're going to expound a little bit on your knowledge of titration curves from Chem 20 and add a little bit more to it here for Chem 30. So this is what the extent of your knowledge was in Chem 20. We had sort of really one titration curve, but if we kind of flip the titrate in the sample, then we kind of got a flipped curve, right? So we've got these two diagrams that shows, okay, if I've got my hydrochloric acid, let's say, or strong acid as my sample, and I'm adding a base to that, then I'm going to get these flat regions where the pH doesn't really change very much, and then with a very small volume, I'm going to get a real big spike in pH, and then I'm going to be up here in the base region of the pH scale. And then if we were to flip the sample and titrate, we'd have that. But the thing, we'd have this curve here. But the thing to point out was that the equivalence point, which is the middle of this peak, is at a pH of 7. And so this shows that the strong acid with the same concentration is being neutralized by a strong base with the same concentration. And also for this. But now that we've learned a lot more about equilibriums and about weak acids and how much they ionize and equilibrium constants and stuff like that, we can now introduce titrations to you that involve weak acids and weak bases. So these are the four kind of monoprotic types of titration curves that you need to know. Monoprotic meaning that it's a substance that can only donate one proton if it's an acid, or only accept one proton if it's a base. And so if I have a titration where I do a titration of a weak acid with a strong base, so I'm adding the strong base to the weak acid, my weak acid pH is going to be higher to start. And then as I titrate this, I'm still going to get this peak and the sharp rise with a small amount of volume, and I'm going to have an equivalence point, which is the middle of that peak. But what you'll notice here is that with a weak acid being titrated with a strong base, the equivalence point is now shifted up into the base region of the pH scale, something above 7. And same thing here if I switch them, but still titrating, or now I'm titrating a strong base with a weak acid, I get my curve that looks like this. I'm going to end off with a pH that's a lot higher than a strong base would have. And so because of that, it shifts my equivalence point above 7 again. If I flip it around to where now I'm titrating with a strong acid with a strong base, you can see that I also get this shift of an equivalence point, but now it's below 7. So you can see on the diagrams here how I have that labeled. And so those are for monoprotic acids and bases that we're using in titrations. Finally, we can do a titration with substances that are polyprotic. So something like the carbonate ion, CO3 2- is considered to be polyprotic because it can accept 2 protons onto it. And because of that, we're going to get 2 equivalence points from that. So you can see here I've got a diagram that shows I've got 2 equivalence points. I'm titrating this weak acid with a strong base in this case, which maybe is carbonic acid, H2CO3. It's got 2 protons that it can donate to a strong base, let's say hydroxide ions, and I would end up with a titration curve that looks something like that. So I'm going to come back with another clip and a little bit more information as it relates to polyprotic titration curves, as well as these monoprotic ones. But specifically certain regions found on these curves, what do they mean, and what do we call them, how do we identify them. So a little bit more information coming your way in the next clip, so hang tight. Be right back with a new example. Buffers and buffer regions is what we're going to talk about in this clip, and you can see I've got some titration curves up here on the board, a little bit enlarged from the ones that we had previously, just so you can kind of see things a little bit better. And then I've labeled some things, and I'm just going to kind of take you through these diagrams a little bit. So first of all, I've got a weak acid reacting with a strong base here. You can see my titration curve with the equivalence point above 7. And then this is the chemical reaction that's occurring, this Bronsted-Lowry equation. And you can see that as I add OH- to this solution, I am going to start making F-. Now at some point in this area right here though, I'm not going to have enough, I haven't added enough hydroxide ions to react all of the hydrofluoric acid molecules that's present in the solution. And so as I start to add OH minus to this solution, I start to have now a solution where I've got a weak acid with its conjugate base in the solution together. And this is what creates a buffer. If you take a look at the definition here, a buffer is a solution that contains a weak acid with its anion or its conjugate base. And so that's how you can identify them, is saying, okay, does this solution contain a weak acid and its conjugate base? And if it does, then you have a buffer. But what does a buffer do? What does a buffer mean? Well, a buffer does just that. It buffers pH. It makes it so that the pH stays at a relatively constant level. And so if I add more hydroxide ions to this, you can notice that the pH stays relatively constant for a set amount of volume. But at some point, if I add enough hydroxide to this, the buffer is going to run out, and then that's when I see a sharp rise in the pH in this titration. So this area right here where the buffer or the pH is relatively constant, that's what we identify as a buffer region. And this is a buffer, a weak acid with its conjugate base. If you take a look at this example over here with the polyprotic weak acid, carbonic acid with a strong base, you can see I've got my two equivalence points. But because I've got these two flat regions here, I've got two different Bronsted-Lowry equations that are occurring. So as I'm adding my hydroxide ions to this, the first reaction that's going to take place is this one where I've got the carbonic acid reacting with the hydroxide. And I make my hydrogen carbonate ions in solution, and so this is a weak acid with its conjugate base, a buffer region. And this is a buffer. You can see the pH stays relatively constant. When I add enough hydroxide though, all of the H2CO3 now has reacted, the buffer has run out, and so I get a sharp rise in pH. But the interesting thing with this one now is now I develop actually a second buffer region here where I get HCO3 minus, which is still a weak acid. It's not a very good one, but it's still a weak acid with its conjugate base. And so because this is the strongest acid that's present in the solution, when I add hydroxide to it, it's now going to start to react with that substance as the Bronsted-Lowry acid. It's going to make the conjugate base and the conjugate acid over there on that side, and I start to get a weak acid with its conjugate base in solution. So this is another buffer region. And so this is actually applicable to humans and our blood. So our blood has to sit within a range of 7.2 to 7.4, and it's a very small range. Anything below or above that is fatal to humans. And so our blood is made up of a variety of different types of buffers, and this is one of them, carbonic acid with hydrogen carbonate ions. And all it really does essentially is this, is that if you ingest something that's acidic, then that acid is going to react with the hydrogen carbonate ions, and those hydrogen carbonate ions are going to turn into carbonic acid, which is a weak acid. If I drink something that's slightly basic, then that carbonic acid is going to react with that base, turning the carbonic acid into hydrogen carbonate ions, and the process just kind of bounces back and forth. And with all these different buffers in our blood, we just kind of move back and forth along these buffer zones and these buffer regions where we are able to kind of maintain a relatively stable pH within our bodies. And the last thing I wanted to point out on these curves is that these regions right here up at the top, these are not considered, they're flat regions, but they're just flat regions because it's just a strong base now. I have a strong base here with no other things that it's able to react with. They've all been neutralized by the strong base. This is just excess stuff. So these top regions over here on the top, these are not considered buffer regions. Okay. If I were to have another titration curve that's a little bit flipped, something like that, then these would be buffer regions, and that final one right there would not be a buffer region. So that's all you got to know about buffers and buffer regions. Some chemical reactions there for you to kind of take a look at and make sure I'm doing them correctly, as well as a little bit of application to our human bodies and the chemistry behind what's going on inside of our bodies is kind of neat to know. So that's all I got for you guys. Thanks for watching.